Thank you so much for joining me. There is a number most people have never heard. A single hyperscale data center today consumes roughly as much electricity as 100,000 households. The next generation of AI computing campuses now under construction will consume individually up to 20 times that amount. That is not a projection for some distant future. That is what is being poured into concrete and steel right now in 2026, and it raises questions almost nobody outside the energy industry is asking today. Or today enough. Where exactly is all of that electricity going to come from? There is a race everyone is watching, and the constraint almost no one is. The public conversation about artificial intelligence is dominated by chips, model parameters, and algorithmic breakthroughs. That framing made sense for years. It is becoming outdated. Every major energy institution now tracking this space. The International Energy Agency, the US Department of Energy, Harvard's own Belfer Center for Science and International Affairs, is covering on the same underlying finding. The physical electricity grid, not computational capacity, is emerging as a binding constraint on how fast artificial intelligence can actually scale. This is not a philosophical concern about AI's environmental footprint. It is a hard engineering and economic bottleneck, with a price tag measured in trillions of dollars, and it's unfolding faster than the infrastructure built to accommodate it. Now we come to the question what the International Energy Agency is actually measuring. Let us start with the global picture. According to the IEA's Energy and AI analysis, global electricity consumption from data centers stood at approximately 415 terawatt per hour in 2024, about 1.5% of all electricity used on Earth. That figure had already been climbing at roughly 12% per year for 5 straight years. Then came 2025. Total data centers electricity demand grew by 17% in a single year. Electricity consumption officially and specifically from AI-focused data centers, not general cloud computing, but AI training and inference, surged by 50% in the same year. In its base case, the IEA now projects global data centers electricity demand to reach approximately 945 terawatt per hour by 2030, more than double the 2024 figure, driven almost entirely by the artificial intelligence alone. These are not activist projections or speculative headlines. This is the International Energy Agency, the same body governments rely on for energy security planning, describing what is, in its own words, a widening gap between the speed of the AI revolution and the speed of the physical systems that have to support it. Now, looking at the America's version of the problem in Berkeley Lab's own numbers. Zooming into the United States, currently the epicenter of AI infrastructure build-out, and the picture sharpens further. The U.S. Department of Energy, through Lawrence Berkeley National Laboratory, found that American data centers consumed about 4.5% of total U.S. electricity in 2023. The projection that share could climb to somewhere between roughly 7 and 12% by 2028, an increase from 176 terawatt per hour to as much as 580 terawatt per hour in just 5 years. A subsequent Berkeley Labs update found that data centers alone could account for roughly a third of all new electricity demand growth in the entire United States through 2030. Here is what the real bottleneck reveals itself. It is not generation capacity in the abstract. It is a connection between new power projects and the grid itself. Berkeley Lab's own tracking found that at the end of 2024, approximately 2,300 gigawatts of proposed generation and storage capacity sat waiting in the US interconnection queues, more capacity than the country's entire existing power fleet, which stands at roughly 1,280 gigawatts. The median wait time from interconnection request to actual commercial operation has more than doubled over the past 2 decades, now averaging around 5 years for recent projects. Set that timeline against the pace of AI infrastructure itself, where a data center campus can go from announcement to operational in 2 to 3 years, and you have what the US Federal Energy Regulatory Commission has explicitly named the central planning problem, where technology is moving on a timeline of months and quarters layered on the top of an electricity grid still built to move it on a timeline of years and decades. The night 60 data the night 60 data centers vanished from the grid. Abstractions like terawatt hours can be hard to feel, so consider that what actually happened in July 2024 in northern Virginia, the single longest concentration of data center capacity on Earth. A voltage fluctuation on the local grid triggered the simultaneous automatic disconnection of 60 data centers at once. In an instant, the grid operator was staring at a 1500 megawatt swing in power balance and had to execute emergency adjustments in real time to prevent that disturbance from cascading into a broader regional outage. It didn't become a headline disaster, it became instead a documented warning, cited by Harvard's Belfer Center as a case study in exactly the kind of concentration risk this build-out is creating. Northern Virginia is not an isolated case. In Ireland, data centers already account for more than 20% of the entire country's electricity demand. And in Dublin, specifically, that concentration approaches 80%, a trajectory Ireland's own energy regulator has publicly flagged as unsustainable. Without major grid reinforcement, in specific, two very different countries on two different continents, covering on the same structural stress point. And they're converging on the same structural stress points as well. What this means if you allocate capital or choose where to build. For anyone making infrastructure investment or site selection decisions, this reframes the AI conversation entirely. McKinsey now estimates that nearly $7 trillion in global infrastructure investment will be required to support this build-out through 2030. That capital is already flowing into gas turbine manufacturing, into next-generation nuclear and small modular reactors, into transmission and grid modernization technology, and increasingly into on-site behind the meter power generation as developers grow tired of waiting years for a grid connection. The IEA notes this dynamic directly. Constrained by slow interconnection timelines, a meaningful share of new US data center projects are now pursuing on-site natural gas generation simply to move forward on a schedule the grid itself can't match. The strategic implication is straightforward. Electricity availability, grid proximity, and interconnection queue position have become as material to AI infrastructure strategy as chip supply or talent access, arguably more so given how much harder physical grid capacity is to accelerate than a supply chain. Any organization evaluating exposure to the AI build-out, whether as a builder, an investor, or a policymaker, is now, whether it recognizes it or not, also in the energy infrastructure business. We tend to imagine technological revolutions as context of intelligence, better models, faster chips, smarter algorithms. The evidence from the world's leading energy institutions tells a more grounded story. This revolution, like every industrial evolution before it, ultimately runs on power, literal, physical, kilowatt per hour power. The organizations that understand this early treat electricity access as a strategic asset rather than a background utility are the ones positioned to keep building when others are left waiting in a 5-year queue. Thank you so much for being here. I'm looking forward your reflections, your comments. Make sure I'll read every one of them. Thanks for watching once again for being present. Till next video.